Have I seen? I think I have seen that movie. It's been a while though. It's you need someone like go around, get out of the way, like seriously. Okay. So not teaching anything new necessarily today, but we are I am going to give you some Delta Math questions today. Which will hopefully help. If there was anything you weren't getting from previous Delta Math assignments, I hope I get it covered here. But there's some very good questions, a lot of calculator work today, so you get that calculator handy. Oh, and by the way, we are using the calculators in geometry now for trig. So they're in degree mode, so you need to switch it back to radians. So,
Mine's a decimal. Does that make a difference? Answers auto.
Okay.
The bottom one down there. There's such a auto. Won't matter.
Interesting. I don't know that it'll matter. Yeah.
Oh, okay.
That would be interesting to see. Oh, interesting. You're floating three decimal places there? Oh, yeah.
Yeah.
You always do that?
Like that.
Okay. You can change it to float, and then, yeah, I wouldn't set it to 3, because I think it stops calculating after 3 decimal places instead of doing like a full 9 decimal points. But I'm not sure. Anyway, all right, here we go. So I chose, this is one example of pretty much, actually, and 2, 3, and 4, I think, are all great problems from one section where you have quite a few things. So it's sort of a mixture today. You do have some things you have to pay attention to. It might ask for a derivative, okay? So pay attention. We have the velocity of a bicycle riding down a straight road is measured by the differentiable function f. F is measured in feet per second, and t is measured in seconds. So what are the units of? So I briefly talked about this yesterday, talking what are the units when we do these things. So this, just looking at it, it looks like an average value. We've got that 1 over b minus a in front, so that's what we learned yesterday. So this is an average value of f prime. The average value of f prime. So it's an average rate of change is what it actually is. So first of all, we know that f is feet per second. What are the units for f prime? How do you figure that out? Isn't that interesting? I chose this one on purpose. So when I'm thinking about my functions, I like to go back to the graph. So we have this function, this f of t function, and its units are feet per second. And then on the horizontal axis, t is measured in seconds, okay? And so what we have is we have some function, I don't know what it looks like, but there it is, there's our function f. Now what we're doing, if we do what this says, we need the derivative of this. Well, what is the derivative? It's a slope. So let's say I take these 2 points here, and I want to calculate the average rate of change, or the slope between those 2 points. Well, slope is the change in the y values. Well, those are y coordinates. So it's the change in y. Well, that would be feet per second, however many units that is, over the change in the x. So the change in the y's over the change in the x's, well, the x-axis, that represents seconds. So the f prime function would have units of feet per second in the y direction and seconds. So feet per second per second. And that's really important to sort of understand. So feet per second are the units of that derivative function. So you really have to be a little bit careful. Then we have here we talked about, integral is really area. So this is our height, the height of our function. And then dt would be the change in the seconds. So that's times more seconds. I'm going to put that as seconds over 1. But then we also have this 1 over b minus a here, the 6 minus 0. Well, what are the 0 and the 6 units? Seconds, yeah. Again, so when we're thinking about the integral function, it's some curve, right? Whatever that curve happens to be, from, in this case, 0 to 6 seconds. And so it's the area from 0, the area under the curve from 0 to 6 seconds. So once again, this is over seconds because the 6 represents units of seconds, okay? And when we multiply all that together, let's see, we get some cancellations here. Times by seconds, divides by seconds, cancels out. What do we end up with? Feet per second, or feet per second squared, yep. Feet per second, or feet per second squared. So again, unit cancellation is kind of a cool thing. This one was probably the most challenging of the ones that I looked through yesterday. Questions on that one? All right, and again, just being able to analyze the units like this can be so helpful because it can really tell you what you need to do. Do I need to take a derivative? Do I need to integrate? Just based on what units they're asking me to find, like how, in this case, they might see how far did they travel. So we'd need to integrate this, again, potentially to get rid of a lot. We'd have to do, for this particular function, we'd have to do a lot of integration. But let's look at 2. A particle travels along the x-axis such that its velocity is given by this crazy function. What is the average velocity of the particle on the interval from 0 to 4? You may use a calculator. So most of what we're doing today is calculator work, and there are lots of problems. So you get 2 free response questions that are calculator-based, right? What I love is how elegant everything looks when you do it. They gave us this model for velocity. We want to know the average velocity. So average velocity would be the function we learned yesterday, 1 over b minus a times the integral from a to b of our whatever function we're using, in this case, velocity. Okay? And so what is my interval that we're interested in? What's my a and b? 0 and 4. So we've got 1 over 4 minus 0 times the integral from 0 to 4 of v of t dt. And this is lovely. This is all you need to communicate on a free response question. You are using the function that they have already named, okay? We can type this into our calculator a bunch of different ways. I'm going to go ahead and put our equation in y equals. So we're going to go to y equals, and we're going to type in t to the 2.4, or in this case, x to the 2.4, sine of 3x. And again, making sure you're in radians, because otherwise your answer will be entirely messed up. They used to grade around that. Like if you used radians, you'd lose a point. You couldn't get full credit, but they'd work with your answer. They aren't doing that anymore because they stated in your like in the directions, they'll state, make sure your calculator's in radian mode. Like they state it in the directions, so now they can say, you know what, if you didn't read the directions, sorry. So you get it wrong fully. So make sure you're in radian mode. Here we go. So what we're going to do then, I'm going to do 1 over 4, and then in my calculator, this is math 9, right? Math 9 is the integral from 0 to 4. And I'm going to do alpha f4 for y1 dx. And we get negative 2.1757-ish. Oh, they want us to round to the nearest thousandth in delta math, so do that, negative 2.176. So sorry, for delta math, you need to follow the directions. That's basically what it comes down to. What I love is just how elegant this is. This is a full 2-point answer on the AP Calculus test. You could also do 1 over 4 times the integral from 0 to 4. You could write in your function, t to the 2.4 sine of 3t dt. You could write it that way if you wanted to and then have your answer. But honestly, the less you write, the better. So this is perfect, okay? As long as you're referencing something that's already been given to you in the problem, it's totally fine to do that. All right, let's look at 3. A particle travels along the x-axis such that its velocity is given by another crazy function. If the position, we have velocity and we have position. Tell me about the relationship between velocity and position. Velocity is the derivative of position, that's right. So if x is my position function, the derivative of our position function is velocity. And that's an important thing to write down on your AP test if they give you that. The derivative of your position function is velocity, because it shows the relationship between the two. That's kind of a nice thing. It says the position of the particle is x equals 5 when t equals 1.5. Well, they're giving us some interesting information there. They're saying that x at 1.5 equals -5. What is the position of the particle when t equals 1? So it wants to know x at 1, and that's what we're trying to figure out here. So we have some information, and if you want to think about it, this is sort of like, hey, they gave us a derivative function. We want to figure out some information about the original function, the antiderivative, okay? This is the fundamental theorem of calculus. So just to write that down, let's see, I'm going to write, if I integrate from a to b of some derivative function, again, I have a derivative function, and if I'm integrating from a to b, it is simply f of b minus f of a. This is the fundamental theorem of calculus that relates a derivative. I can take the antiderivative of it and get my original function. Well, that's exactly what we're doing here. We're starting with velocity. And if I integrate velocity, that's going to give me position. Okay? So I'm going to write that down. If I say I have my integral from 1 to 1.5, because those are the time values they're giving me. If I integrate velocity, that's going to equal x of 1.5 minus x of 1. The antiderivative of velocity is position. All right, this is just the fundamental theorem of calculus again. So what can we plug in? Well, we know a lot here. I know that x of 1.5, I know what that is. And I'm trying to figure out x of 1. All I need to do is isolate x of 1. I'm going to go ahead and add x of 1 to the left and subtract my integral. I'm going to do a little switcheroo here. So x of 1 equals x of 1.5 minus my integral from 1 to 1.5. Now again, there's a ton of different ways to do this. They don't do this exactly the same way in Delta Math, but I'm always going to start with the definition, the fundamental theorem of calculus, and rearrange. All right, so I'm trying to find x of 1. I know that x at 1.5 is -5, and then this monster here, I can plug all this into my calculator. So that's what I'm going to do. So in my calculator, I'm going to go back to y equals, I'm going to type in my velocity function here. X of 0.8, x to the 0.8 plus 5 sine of 3x minus 1. I think I got it. Take your time when you're typing those things in. I tend to put 0.08 instead of 0.8, so be careful. I'm going to quit, and then I'm going to go ahead and just type this in, -5 minus math 9, my integral from 1 to 1.5 of y1 in terms of x. And so x of 1 equals negative 6.464. And they did want us to round to the thousandth, so that is rounded to the thousandth place. Again, I just really love how elegant the math is. You don't have to start with the fundamental theorem of calculus in this form. You can rearrange it and do start plus, or in this case, start minus. But you'll never get it wrong if you just always write it with the fundamental theorem of calculus. All right, any questions on that one? Are you okay with my rearranging? Adding the x of 1, subtracting the integral. Okay, I think it's a good skill. All right. Number 4, a particle travels along the x-axis such that its velocity is given by another big crazy velocity equation. Find all the times when the speed, speed. What is, like we're looking at a velocity curve, maybe we should look at it. Let's go ahead and type it in. X to the 2.4, sine of t plus 2. All right, I'm going to delete that for a minute. My interval is from 0 to 6. So I want my window to be from 0 to 6. I have no idea what my y min and y max should be, so I'm just going to go from negative 10 to positive 10. Let's take a look at this function. So this is a velocity curve, but we're interested in when the speed. Tell me about the relationship between speed and velocity. Speed is the absolute value of velocity. So let's talk about for a minute, just to remind you, what is velocity telling me? It's telling me speed with direction. All right? So for instance, this particle is moving along the x-axis. It's moving left and right. Okay? So when our velocity curve is positive, we are moving to the right. When our velocity curve is negative below the axis, then we are moving to the left. All right? So velocity curves tell me when we're moving left and right in this particular case. If we were moving horizontally, would be when we're moving up and down. Okay? So positive and negative, in this case, refer to moving left or right. Yeah. Okay. Thank you. Okay. I have no idea what to do with this. All right. So what we want to know is when we have a speed. Well, that means we could be going 3 units or 3 inches per minute or whatever it happens to be, right? Whatever speed we're going 3 units per time measurement to the right, or we could be going 3 units per time to the left. All right, so it could happen twice. We want speed is the absolute value of velocity, okay? So we could do a couple of things here, but I am just going to go ahead and then, no, I don't want to do that. Let's do, well, we want to find all the times. If I were to write this down, I'd want to know when the absolute value of velocity equals 3. That's what we're trying to figure out. That's a great equation. But we could also, or do it this way, we could say where does v of t equal 3, or where does v of t equal negative 3? Because those would be a speed equal to 3 in either case. One just means 3 we're moving to the right, and 3 we're moving to the left, okay? So let's do that, because I'm already here. I'm going to do 3, and I'm going to do negative 3 in my y equals. And I'm going to graph those. And you can see there's 3 intersections here. So we need to find all those intersections. So we're going to calculate the intersection. So calculate number 5. And I'm just going to move Tinkerbell to my black line using the up and down arrows. And do enter, enter, enter. So we get t equals 1.871. I am rounding to the nearest thousandth. I'm going to do it again, calculate. I'm going to move Tinkerbell to my black line. Enter, enter, enter. I get 4.187, rounding that one. And then calculate again, moving to the red line, and now moving over to the intersection. Whoops, no sign change. They didn't. Sorry, I was on the wrong curve. Calculate, number 5. I got my blue. I have to be on the blue line and the red line. I overlooked that. There we go. There we go. Now that intersection, 4.370. Originally I did the absolute value in there. So if I were to do that, I would insert, let's see, math, num, absolute value. Oh, damn it. Damn. I thought it would just do it the old school way. Whoops. But no. All right. So I'd have to retype this. X to the 2.4. You can see the graph will look a little bit different, but all it's going to do is make everything that was negative flip up and turn positive. So now it looks like that, where it flipped up that negative portion, just flipped it straight over, reflected it over the axis. We'll get the same exact x values at that intersection there. Okay? So a couple of different ways to do that. Let's look at number 5. I like number 5. It's kind of interesting. We are looking at the graph of f prime. So we're looking at a derivative function. The derivative of f is shown in the graph below if f of 6 equals 5. So again, they are giving me an original function, not a derivative value. They're giving me the original value again. We want to know again, what is the value of f of negative 5? This is again that fundamental theorem of calculus. If I take my derivative function and integrate it with these given t values, maybe, I don't know, see, negative 5 to 6, then that should give me, if I take the antiderivative of a derivative function, they cancel out, leaving me with just f of 6 minus f of negative 5. So again, this is the fundamental theorem of calculus. Look at what they give you. Did they give you a derivative? Then we need to integrate it. Okay? Now, we are trying to figure out f of negative 5. So once again, I'm going to add that f of negative 5 to the left and subtract my integral. So I have f of negative 5 equals f of 6 minus the integral from negative 5 to 6 of f prime of t dt. If you wanted to use f of x dx, that's also fine. They won't care. Okay, so if I want to find f of negative 5, I know f of 6. F of 6, they told me, was 5. Now, then we have to integrate from negative 5 to 6 of f prime of t dt. Wait a minute. How do I integrate that? Like, what does this really mean? Area under the curve. That's right. This is area. So we need the area under the curve for between negative 5 and positive 6. So we have two areas here. What's the area of this first triangle? Times 4. So we get 10 for the area of that triangle above there. And then this one, again, 1/2 base times height. The base in this case is 6, and the height is 6. So this area is 36, but it is below the axis, so we give it a negative. We do need to be careful. This is why I liked this problem, because we are subtracting everything. So I have 5 minus. The area here would be 10 minus 36. but we have to subtract everything. So you do need to be very, I did not do that right. It'd be 18. Sorry. Sorry, that's 18. I was like, wait a minute. Forgot one step there. There we go. Thank you, guys. 10 minus 18, which is negative 8. So that becomes 5 plus 8, which gives me 13 for f of negative 5. F of negative 5 is going to equal 13. That looks like a B, but it's a 13. Okay. All right. How do you feel about that fundamental theorem of calculus? Is it sort of starting to engage a little bit?
Yeah.
Yeah? It's a tough one. But once you get it, it's like, oh, yeah, okay. All right. Number 6, the velocity of an object moving in a straight line in meters per minute can be modeled by the function v of t, where t is measured in minutes. Selected values of v of t are shown in the table. Approximate the value of 1/12, the integral, from 0 to 12 of v of t dt. Again, what is that 1/12 in front telling you that this is? Average value. All right, this is the average value of velocity, and that's important to recognize. Using a midpoint Riemann sum with 3 subintervals of equal length. All right, if we're doing 3 subintervals of equal length, oh, what is our change in t? Well, the interval is 12 minus 0, and we want 3 subintervals, so how long is each interval? 4. All right, so we have an interval from, we're going to go from 0 to 4, 4 to 8, and then 8 to 12, so those all have a width of 4. How do we find the midpoint? It's given. Yes, they lovingly gave us the information we needed. Between 0 and 4 is the midpoint too, and we want to use that corresponding output value for our height of our rectangles. Between 4 and 8, the midpoint is 6, so we're going to use that height value of 3. And between 8 and 12, we're going to use the output at 10, of 10. So to get 1/12, the integral from 0 to 12 of v of t dt, we are going to approximate it using our Riemann sum. So I'm going to keep that 1/12 out in front. And again, this is just area. We need a height value, that's the v of t. And we need a width value, that's the change in t here. So I have a width of 4 and a height of 8, plus another width of 4 and a height of 3, plus the other width of 4 and the height of 10 for that midpoint Riemann sum. And again, you know, on an AP test, if you needed to draw a little graph, connect it with lines, if you know, little straight lines, and then you can draw your boxes. Like, you know what it should look like if you're having trouble figuring out, you know, in the heat of the moment, what exactly you need to do. Draw a picture. When in doubt, graph it out. That's what I always say. This is 32 plus 12 plus 40, which is 84, and then 1/12 of that is 7. All right, any questions for me? All right, super. So it is sort of a review assignment, which is kind of nice. But hopefully it sort of synthesizes some things for you. Good luck.